Hello and welcome. Settle in and make yourselves comfortable. Tonight we journey far beyond our planet, past the edges of our galaxy, deep into the very largest structures imaginable. What if I told you that the universe is not chaotic? That within its most gigantic scales there lies an order, an almost intelligent pattern, a structure so immense scientists speak of it in hushed tones, almost a whisper, calling it the architecture. Today we are going to discuss a forbidden discovery, a finding that fundamentally challenges the core principles of modern cosmology. We will journey to witness cosmic megastructures that, according to everything we know, should not exist. Prepare yourselves, because this sleep lecture might just keep you wide awake as we uncover the mystery hidden within the dark depths of the cosmos. To truly grasp the magnitude and shocking nature of this discovery, let's momentarily step back in time. Just a century ago, we believed our Milky Way was the entire universe, a solitary stellar island floating in a boundless void. It wasn't until the pioneering work of Edwin Hubble in the 1920s that we realized those fuzzy patches in the night sky were, in fact, other distant galaxies just as vast as our own. The universe suddenly expanded its boundaries. But even then we pictured the cosmos like a kind of soup, where galaxies were more or less evenly distributed, a random, chaotic jumble of star systems. We assumed that if you took a large enough cube of space, the density of galaxies within it would be roughly the same, no matter where you placed that cube. This concept, known as the Cosmological Principle, formed the absolute foundation of our understanding of reality. But then, as more powerful telescopes and advanced methods of mapping the universe became available, this simple, convenient picture began to crack. Astronomers started seeing patterns. It all began right here, in our cosmic backyard. When astronomers started charting the locations of our closest galactic neighbors, they quickly noticed that these galaxies weren't scattered randomly across space. Our own galaxy, the Milky Way, along with Andromeda and roughly 50 smaller satellite galaxies, constitutes what scientists call the local group. This isn't just a random cluster, it's a gravitationally bound system where all members orbit a common center of mass, situated somewhere between the Milky Way and Andromeda. This provided the first clear evidence that the universe had structure. Think of it like a small town or village where several houses are clustered together, forming a single community. That's essentially our local group. Its size is already staggering, spanning about 10 million light-years across. It takes light 10 million years just to cross this backyard, but this was only the start. Astronomers realized that to grasp the full cosmic picture, they needed to widen their scope considerably, so they began mapping not just individual galaxies, but entire groups similar to the one we inhabit. And what they found forced them to completely rethink everything they knew about the cosmos. Scaling up once more, scientists realize that our own local group is merely a modest suburb within a gigantic cosmic metropolis. This metropolis is known as the Virgo supercluster. It encompasses over 100 galaxy groups and clusters, including ours, and its core lies roughly 65 million light-years away from us, in the direction of the constellation Virgo. At the very heart of this supercluster sits the massive Virgo cluster itself, cramming more than 1,000 galaxies into a relatively small volume. This cluster acts as the undisputed gravitational epicenter for our entire cosmic neighborhood. All the galaxies here, including our own, are slowly but surely being drawn toward it, much like vehicles converging on the downtown core of a major city. The Virgo supercluster stretches approximately 110 million light-years across. At this scale, the universe ceased to resemble a uniform soup. Instead, it looked like a detailed map of a country, featuring clusters as major cities, groups as towns and individual galaxies as scattered houses. But even this perspective didn't provide the complete picture. The lingering question was, what existed in the vast spaces between these cosmic cities? Were they truly isolated islands, or was there something connecting them all? The answer to this question arrived with the rise of technologies that allowed us to measure the distance to a massive number of galaxies. This method is known as the measurement of redshift. Because the universe is expanding, the farther away a galaxy is, the faster it recedes from us. The light emitted from that galaxy stretches, shifting it toward the red end of the spectrum. By measuring this shift, we can calculate the distance. By conducting these massive sky surveys, astronomers, acting as cosmic cartographers, began creating three-dimensional maps of the universe, and it was then that a truly breathtaking picture appeared before them. They realized that superclusters of galaxies were not isolated islands. They were merely the brightest and densest knots within a colossal, all-pervasive network. This network was dubbed the cosmic web. It is composed of long, delicate structures that stretch for hundreds of millions of light years. These structures are known as galactic filaments. They resemble glowing fibers connecting massive clusters like highways between major cities, and the galaxies themselves, as we've noted, are like pearls strung along these invisible threads. Our own local group resides within one of these filaments. We live on the outskirts of a cosmic metropolis, situated right on one of its main transport arteries. The first true shock, the structure that truly forced scientists to question their existing models, was the CFA-2 Great Wall. Discovered in 1989 by Margaret Geller and John Huchra, this immense structure materialized during a redshift survey at the Harvard-Smithsonian Center for Astrophysics. As they mapped thousands of galaxies, a gargantuan structure revealed itself before their eyes. It was a flat, elongated structure composed of galaxies, superclusters, and filaments. It measured 500 million light-years long, 300 million light-years wide, and yet only 15 million light-years thick. Imagine a colossal wall constructed entirely of galaxies. Its sheer size defied belief. Based on prevailing theories, the universe, at 13.8 billion years old, simply hadn't existed long enough for gravity alone to assemble something so massive and so organized. The discovery was the equivalent of stumbling upon a perfectly straight, pristine highway running through the middle of a primeval wilderness. The initial reaction from the scientific community was pure skepticism. Could it be a simple observational error, an optical illusion? But subsequent research confirmed the truth. The wall was real. And as it turned out, this was only the beginning. The obvious question is, how do scientists actually manage to create these kinds of maps? It's not like we can hop on a starship and map the universe directly. The process is incredibly painstaking and requires decades of meticulous effort. As we mentioned, the core tool is redshift. A telescope is aimed at a specific patch of sky where it performs a spectral analysis of light coming from thousands of galaxies simultaneously. We measure the redshift for each galaxy, which gives us its distance, that all-important third coordinate, depth. The telescope then shifts to the next segment, and the process repeats. This is how astronomers, step by step, layer by layer, build these massive three-dimensional maps. Landmark projects, such as the Sloan Digital Sky Survey, or SDSS for short, have already catalogued millions of galaxies, letting us gaze billions of light-years into the past and deep into space. This is essentially cosmic archaeology, but instead of digging through layers of Earth, we are digging through layers of time. The further we look, the younger the universe we observe. And these maps quickly demonstrated that the CFA-2 Great Wall was far from being the largest structure in the universe. its record was soon broken. In 2003, data from the renowned Sloan Digital Sky Survey led to the discovery of an even more grandiose structure, the Sloan Great Wall. It measured an astonishing 1,370,000,000 light-years in length, nearly 3 times longer than any similar structure previously known. To truly grasp this scale, consider this analogy. If our entire Milky Way galaxy was shrunk down to the size of a coin, the Sloan Great Wall would stretch the length of a football field. This colossal structure is a gigantic galactic filament, one of the massive threads woven into the cosmic web, a feature instantly visible on the universal map. At the time, it was officially the largest object known to science. Its very existence immediately presented cosmologists with profound and uncomfortable questions. How could such an enormous and highly ordered structure have possibly formed within the lifespan of the universe? The standard cosmological model, which describes the evolution of the universe since the Big Bang, began to show cracks when attempting to account for the formation of such mega-objects. It became clear that there was a fundamental gap in our understanding. A crucial missing element of the cosmological puzzle remained stubbornly elusive. However, the cosmic web is more than just filaments and sheets. An equally important and mysterious part of this structure are the voids. These are gigantic, almost completely empty regions of space situated between the filaments. If galaxy clusters are the cities and the filaments are the roads connecting them, then the voids represent the vast, uninhabited countryside. Their scale is just as staggering as the sheets they separate. A typical void measures anywhere from 100 to 300 million light-years across. Inside these areas, there are virtually no bright galaxies. They are like giant soap bubbles where all the visible matter, the galactic filaments, is concentrated along their surfaces. In fact, the voids themselves occupy the vast majority of the universe's volume. Galaxies and their clusters are nothing more than a thin film lining the walls of these massive bubbles. Studying these voids is just as crucial as studying the surrounding structures. Their shape, size, and distribution carry crucial information about the universe's earliest moments, revealing the nature of the mysterious forces that shaped this structure, namely dark matter and dark energy. Ultimately, the absence of matter turned out to be just as informative as matter itself. So what exactly is this invisible sculpture that carved out this grandiose cosmic architecture? According to the leading scientific theory, the answer lies in dark matter. It's a mysterious substance that neither emits, absorbs, nor reflects light. We can't see it directly. We only know it exists because of its powerful gravitational influence on visible matter, the stars and galaxies. Dark matter accounts for about 27% of the total mass energy of the universe. Meanwhile, the ordinary visible matter, the stuff that makes up you, me, the planets, and the stars, is just 5%. The theory posits that dark matter forms the invisible framework or scaffold for the entire cosmic web. Immediately following the Big Bang, there were tiny fluctuations in the density of dark matter distribution. In the areas where the density was slightly higher, gravity started pulling harder, attracting more and more dark matter. Over time, these regions eventually collapsed into what we call filaments and nodes, and the ordinary baryonic matter simply followed suit, much like iron filings drawn to a magnet, concentrating in these gravitational wells to form the galaxies and their clusters we see today. The crucial evidence for this theory emerged from the world of computer modeling. Scientists designed incredibly sophisticated simulations, starting just moments after the Big Bang and tracing the universe's evolution across billions of years. These simulations incorporate the known laws of physics, along with the hypothesized properties of dark matter and dark energy. One of the most famous of these is the Millennium simulation, which followed the fate of over 10 billion particles within a spatial cube spanning 2 billion light-years. And the results were stunning. Based purely on gravity and the assumed characteristics of dark matter, the computer model, running autonomously, without any manual fine-tuning, reproduced a structure uncannily similar to the observed cosmic web. The same filaments, walls, and immense voids that astronomers had observed through their telescopes manifested themselves on the computer screens. This provided the most compelling evidence yet that the invisible framework of dark matter is truly the scaffold underpinning the entire large-scale structure of the cosmos. It appeared the puzzle had been solved, or at least almost solved. But where did those initial density fluctuations, the very seeds for future galaxies and clusters, actually originate? Scientists believe the answer lies in the earliest moments of the universe. For the first 380,000 years after the Big Bang, the universe was filled with a hot, dense plasma made up of protons, electrons, and photons. This plasma was so incredibly dense that light couldn't travel freely through it. Within this plasma, which behaved like a gigantic boiling cauldron, sound waves raged, surprisingly similar to how sound travels through the air today. These waves, caused by the interplay between gravity and radiation pressure, are known as baryon acoustic oscillations, or BAO. They created areas of slightly higher and slightly lower density. When the universe cooled sufficiently for protons and electrons to combine into neutral hydrogen atoms, it suddenly became transparent to light. This first light, which has traveled to us over billions of years, is what we observe today as the cosmic microwave background, CMB radiation. And on the map of this background radiation, we can clearly see the imprints of those sound waves, the faint ripple marks left behind by that primordial plasma's boiling. Crucially, these waves imprinted a fixed scale, essentially leaving a cosmic ruler for the universe, and it is at this specific separation distance that we are statistically most likely to find galaxies clustered today. This effect is the original cosmic blueprint, the foundational template upon which all subsequent cosmic architecture was built. It seemed we had a beautiful and coherent theory. The initial sound waves in the young universe created the blueprint. Dark matter built an invisible scaffold according to that design, and visible matter filled it in, creating the cosmic web. This model perfectly described structures, even those as massive as the Sloan Great Wall. But then in 2013, a discovery completely shattered that perfect picture. A group of astronomers studying the distribution of gamma-ray bursts, the most powerful explosions in the universe, usually thought to occur randomly, stumbled upon something unimaginable. They found a massive cluster of these gamma-ray bursts in one specific region of the sky, indicating a structure of unbelievable size. They named this structure the Hercules-Corona Borealis Great Wall. Its estimated size, 10 billion light-years, 10 billion light-years. That is nearly 10% of the diameter of the entire observable universe. This discovery wasn't just a new record, it was a direct challenge to the foundations of modern cosmology. To understand why the Hercules-Corona Borealis Great Wall posed such a serious problem, we need to revisit the Cosmological Principle. As a reminder, it essentially states that on sufficiently large scales, the universe is homogeneous and isotropic. That is, it looks the same in every direction and at every location. This is the fundamental assumption underlying all of Einstein's general relativity equations that describe the universe as a whole. Of course, the universe is not uniform on smaller scales, those of planets, stars, and galaxies. But it was believed that if you took a cube of space several 100 million light-years across, the matter within it would already be distributed quite uniformly. There was even a theoretical limit for the size of the largest possible structures, known as the scale of homogeneity. Estimates place this limit at approximately 1.2 billion light-years. Any structure larger than this size simply shouldn't be able to exist, as it would be a direct violation of the cosmological principle. Yet the Hercules-Corona Borealis Great Wall turned out to be almost 10 times larger than this theoretical maximum. Finding it was the equivalent of discovering a wave several kilometers high rising out of an otherwise perfectly smooth ocean surface. The very existence of a structure as gigantic as the Hercules-Corona Borealis Great Wall directly challenges the standard cosmological model. According to this model, the universe simply hasn't existed long enough to form an object like this. Gravity would need tens, if not hundreds, of billions of years to pull matter together into such a colossal filament. Yet the age of the universe is only 13.8 billion years. This means one of two things. First, the discovery might be a statistical error, a random cluster of gamma-ray bursts that we've misinterpreted as a unified structure. Many scientists hold this view, pointing out that the method of detection relying on gamma-ray bursts is not as reliable as direct mapping of galaxies. Or, the alternative is that our fundamental model of the universe is either incorrect or, at the very least, incomplete. And it is this second possibility that makes the discovery forbidden. It forces scientists to move beyond established theories, compelling them to consider the boldest, even heretical, ideas about how our universe is truly structured. This is the very kind of anomaly that could lead to a scientific revolution. If the standard model can't account for such gargantuan structures, what alternatives do we have? One key idea is that gravity itself might not behave according to Einstein's predictions when operating across extremely large scales. This has led to the development of so-called modified gravity theories, take MOND, or modified Newtonian dynamics, for example. MOND posits that at the extremely low accelerations typical of the outskirts of galaxies and intergalactic space, the force of gravity actually weakens with distance much slower than we currently believe. This mechanism would allow us to explain galactic rotation without invoking dark matter, and it might even speed up the formation of these large-scale structures. Other theories introduce extra fields or spatial dimensions that only become apparent across cosmological distances. While currently on the scientific periphery, these ideas are complex and don't always align perfectly with every observation. However, their very existence suggests that a major crisis is brewing within cosmology. The presence of these impossible objects is forcing physicists to search for new physics, physics that must transcend the limits of both the standard model and general relativity. It's crucial to understand that science is not a collection of rigid, fixed dogmas. It is a dynamic, living process filled with debate, discussion, and the competition of ideas. The discovery of the Hercules-Corona Borealis Great Wall ignited fierce debates within the scientific community, debates that haven't subsided even now. On one side, we have the proponents of the standard cosmological model. They argue that this structure is likely a statistical artifact and insist we must wait for more precise data from future sky surveys that will either confirm or refute its existence. They point to the immense success of the standard model in explaining a multitude of other phenomena, ranging from the cosmic microwave background to the abundance of light elements throughout the universe. On the other side are scientists who believe that too many anomalies have accumulated to simply be ignored. They view these gigantic structures as clear evidence that our current theories are fundamentally incomplete. This disagreement is not a sign of science's weakness. On the contrary, it is its main driving force. It is precisely at the intersection of established theories and unexplained facts that new, more refined worldviews are born. And we are witnessing one of these pivotal moments in the history of cosmic understanding. Let's take a moment to consider why scientists, even in private conversations, use a seemingly unscientific term like architecture. The word itself carries connotations of order, intention, and design. Now, of course, no serious scientist is suggesting that these cosmic structures were literally built by someone, but the term perfectly captures the feeling you get when you look at a map of the universe's large-scale structure. It's not chaos, it's not a random pileup, it is a system. It has its own elements, nodes, filaments, walls, and voids. It has its own clear hierarchy, and it operates according to specific rules and laws. It looks more like the neural network of a brain or the root system of a gigantic tree than anything we would expect from the blind forces of nature. The word architecture is ultimately an acknowledgement that the universe, at its largest scales, possesses an astonishing degree of complexity and order. And this order demands an explanation, perhaps a far deeper one than we can currently grasp. This discussion about cosmic architecture inevitably leads us to one of physics' deepest mysteries, the fine-tuning problem of the universe. Essentially, it hinges on the fact that fundamental physical constants, such as the speed of light, the gravitational constant, or the mass of the electron, possess the exact values required for the existence of complex structures, stars, planets, and, ultimately, life itself. If even one of these constants were slightly different, the universe would be completely unrecognizable, perhaps starless, chaotic, or utterly sterile. The formation of such a complex and ordered cosmic web also fundamentally relies on this delicate calibration. This raises the crucial question, is it merely an unbelievable stroke of luck that we ended up with this specific universe, or is there some deeper, underlying principle at play? Some physicists hypothesize the existence of a multiverse, suggesting an infinite array of universes with varying physical laws, and we simply happen to reside in the one where conditions were suitable for us. Others, however, see this as an indication that our current understanding of the laws of nature is still superficial, believing that a unified theory exists from which all these constants must uniquely and definitively be derived. When faced with the incredible complexity and inherent order of the cosmic web, more radical, almost fantastical ideas come to mind. One of these is the simulation hypothesis. This philosophical concept proposes that our entire reality is actually an artificially created computer simulation. While famously popularized by the movie The Matrix, this idea is actually seriously discussed by philosophers and physicists alike. Within the framework of this hypothesis, the ordered structure of the universe might not be the result of natural evolution, but rather a consequence of fundamental rules or algorithms set by the simulation's creators. Perhaps the cosmic web is simply the most efficient way to distribute computational resources within this gigantic program. Of course, this is pure speculation, something that for now we can neither confirm nor definitively disprove. But it certainly forces us to question the nature of reality itself and what might lie beyond our habitual perception of the world. What if the laws of physics are nothing more than lines of code? Naturally, when we discuss cosmic architecture, we can't avoid the most exciting and controversial question. What if these truly are architectural structures? What if these colossal formations are artificial? This idea, of course, is far outside the realm of mainstream science, belonging more to the territory of ufology and hard science fiction. It's nearly impossible to conceive of a civilization capable of manipulating matter on the scale of billions of light years. That would require energy sources and technologies we literally cannot even begin to imagine. Nevertheless, as a thought experiment, the concept is absolutely fascinating. Could these structures have been engineered by some ancient, utterly incomprehensible form of intelligence, like massive engineering projects designed perhaps to move energy or information across the cosmos? Currently, science offers zero evidence to support such claims. However, the sheer existence of these impossible structures leaves a tiny crack open for the most unbelievable speculation. It serves as a stark reminder of just how little we truly know, and that the universe might be a far stranger and more wondrous place than we currently comprehend. There are even more exotic theories, though entirely scientific, that attempt to explain the anomalies we see in the universe's structure. One such theory is conformal cyclic cosmology, proposed by the renowned physicist Roger Penrose. According to this hypothesis, our universe is just one link in an infinite sequence of cycles, which Penrose calls aeons. The end of one aeon, when the universe has expanded into an extremely cold and highly rarefied state, marks the beginning of the next cycle, a new Big Bang. And as Penrose argues, information from the preceding aeon can actually leak or filter into our own. He suggested that certain anomalies we observe in the map of the cosmic microwave background radiation, or CMB, might be the residual traces of gigantic black hole collisions that occurred in the universe's previous cycle. It's even possible that some of the gigantic structures we observe aren't new formations of our current aeon, but rather ghosts or scars inherited from the universe that came before. This theory is highly complex and controversial, but it clearly illustrates the intellectual lengths to which scientists will go to explain phenomena that simply do not fit within the standard cosmological framework. Another mystery potentially connected to the universe's large-scale structure is the so-called cold spot. The cosmic microwave background map is generally incredibly uniform, yet there is one region that is inexplicably colder than the surrounding background. Statistically, the probability of such a cold spot appearing purely by random chance is extremely low, and for a long time this remained one of the key enigmas in cosmology. However, recent studies revealed that directly behind this cold spot lies a colossal void, the Eridanus supervoid. This is one of the largest voids known to science, stretching nearly 1 billion light-years across. One theory suggests that as the cosmic microwave background photons traverse this immense emptiness, they lose a portion of their energy, which is what causes that specific region of the sky to appear colder. If this holds true, it would offer direct evidence of the influence of large-scale structure on the very first light in the universe. But some scientists take it further, suggesting that even a void of this immense size cannot entirely account for the cold spot effect. This is where the boldest hypotheses emerge, for example, the idea that the spot is a cosmic bruise left by the collision of our universe with another parallel universe. But that's just one of the strange phenomena associated with the cosmic microwave background. There's another anomaly which has been unofficially dubbed the axis of evil. The issue is this. When scientists took a detailed look at the CMB's temperature fluctuations, they discovered a preferred axis. The fluctuations seem to align themselves around this axis in a way that is distinctly non-random. The truly bizarre part is that this axis appears to be aligned with the plane of the ecliptic, the very plane where our solar system's planets orbit. This directly violates the Copernican principle, which states that our location in the universe is not special or privileged. On the scale of the entire cosmos, we shouldn't be seeing any preferred directions linked specifically to our local system. Researchers have tried to write it off as errors in satellite data processing, or perhaps signal contamination originating from our own galaxy. Yet to this day, no convincing explanation for this anomaly has been found. It's another small but alarming warning sign suggesting that our current cosmic model might be incomplete. Perhaps the large-scale structure of the universe holds even deeper and stranger secrets than we currently dare to imagine. So, what does the future hold? How can we unlock the mystery of the universe's architecture? The answer, as is so often the case in astronomy, lies in new and more powerful tools. The James Webb Space Telescope is already allowing us to peer back into the universe's earliest epochs and witness the formation of the very first galaxies. Specialized missions such as the European Space Telescope Euclid are specifically designed to chart the most accurate and detailed three-dimensional map of the cosmos, plotting billions of galaxies across it. This data will allow us to measure the parameters of the cosmic web with unprecedented precision, test the existence of the largest known structures, such as the Hercules-Corona Borealis Great Wall, and perhaps even uncover new and even more astonishing objects. We are truly living in a golden age of cosmology. Never before in human history have we possessed such powerful instruments for studying the universe, and it is entirely possible that the answers to many of the questions we are asking today will be found within the next few years or decades. There is yet another problem, one that is indirectly related to our understanding of the large-scale structure of the universe. This is known as the Hubble tension. The core issue is that we currently have two primary ways to measure the universe's current expansion rate, which we express through the Hubble constant. One method relies on observing the cosmic microwave background, essentially looking back at the earliest moments of the universe. The second method relies on observing objects in the local modern universe using standard cosmological markers like supernova or Cepheid variables. The problem is that these two measurement techniques yield fundamentally different results. While the discrepancy isn't massive, it is statistically significant and has stubbornly persisted despite our attempts to refine the data. This crisis in cosmology suggests that our current standard model, the one linking the early universe to the late universe, is missing a crucial ingredient. Perhaps the properties of dark energy have changed over cosmic time, or maybe there is a new, unknown type of particle influencing expansion. Either way, the solution to this puzzle will almost certainly be intimately linked to how we understand the formation and evolution of the gigantic cosmic architecture we observe today. And of course, we cannot overlook the principal conductor of the modern cosmic orchestra, dark energy. If dark matter acts as the sculptor pulling matter together into filaments and walls, then dark energy is the relentless force determined to rip it all apart. It's what causes the universe to expand at an accelerating rate. If dark energy maintains this trajectory, the distant future holds a scenario where it severs all gravitational bonds. First, superclusters will dissipate, followed by galaxy clusters, and eventually the galaxies themselves. Ultimately, star systems, planets, and even the very atoms will be violently shredded. This ultimate outcome is chillingly known as the Big Rip. Therefore, the majestic cosmic architecture we observe today is merely a temporary phase. It is the result of a profound cosmic struggle, gravity trying to knit everything together versus dark energy striving to push it all apart. We are living in a unique epoch, the time when this structure is most pronounced and available for us to study. Tens of billions of years from now, however, not a trace of it will remain, just a cold, dark, and utterly empty universe. So, what does all this truly mean for us? Where exactly do we fit into this colossal scheme? The realization that we are woven into this cosmic web fundamentally changes how we see ourselves. We aren't simply living on a planet orbiting a star, lost on the fringes of one of hundreds of billions of galaxies. We are embedded within a structure. Our galaxy is not some lone grain of sand lost in an endless desert. It is part of a gigantic, interconnected organism. We reside within a galactic filament which is itself a part of the Virgo supercluster. And that is just a component of an even greater structure called Laniakea. This awareness gives us a profound sense of belonging. We are not isolated amidst the chaos. We are part of an order whose true scale our minds can barely begin to grasp. It makes us feel both vanishingly small and yet fundamentally integral to something truly magnificent. Our true home isn't just the Earth or even the solar system. Our home is this entire cosmic architecture. Yet another striking observation noted by many scientists and philosophers is the profound similarity between the universe's large-scale structure and patterns found throughout other domains of nature. The cosmic web, defined by its nodes and filaments, bears a striking resemblance to a human brain's neural network. It mimics the root system of a tree, the growth patterns of a slime mold colony, or even the underlying architecture of the Internet. This phenomenon, where similar patterns emerge across vastly different scales, is known as fractality. Naturally, this might just be a coincidence, a mere outcome of similar underlying principles, such as the optimization and efficiency of connections, leading predictably to similar organizational forms. But it could also be a powerful hint at a deeper, universal law governing the organization of matter, a law that applies uniformly from the microcosm all the way up to the macrocosm. Perhaps the universe is, in fact, a kind of gigantic, self-aware brain or living organism, and we are merely the tiny components attempting to comprehend the nature of the whole. All these discoveries and mysteries bring us face to face with a fundamental question: the limits of human understanding. We build models and theories to try and describe reality, but we must never forget the classic dictum: the map is not the territory. Our theories are merely approximations, tools that work brilliantly, but only within specific, defined boundaries. When we push the boundaries to extreme scales like 10 billion light-years, it should come as no surprise that our standard instruments begin to break down. Can we, as creatures whose entire cognitive framework was shaped purely for survival on one small planet, fundamentally grasp the true overall nature of the universe? Perhaps certain aspects of reality are destined to remain perpetually beyond our comprehension, and that is perfectly okay. On the contrary, it is precisely this realization that makes science so profoundly compelling. It is an infinite journey where, behind every open horizon, a new vista, more mysterious and beautiful than the last, awaits us. So why is this discovery labeled forbidden? Naturally, we're not talking about some global conspiracy where scientists are hiding the truth from humanity. The secrecy here is of a different kind. This knowledge is forbidden in the sense that it shatters our comfortable, established view of the world. It forces us to admit that our most fundamental theories, the very bedrock upon which modern physics is built, might be wrong or at the very least incomplete. This knowledge is inconvenient. It creates a crisis, forcing us to re-examine the foundations of our understanding, and that is always a painful process for the scientific community. It opens the door to the boldest, even heretical ideas, concepts that were previously relegated solely to the realm of science fiction writers. The prohibition here isn't an external command, it's an internal barrier, a fear of the unknown that arises when we reach the very edge of the map of our knowledge and look into the abyss of what we don't yet comprehend. This is the ultimate challenge the universe poses to our intellect. As we look ahead, we can only begin to guess what other surprises the universe holds in store for us. As our telescopes become sharper and our maps grow more detailed, we will undoubtedly uncover new, even stranger, and ultimately unexplainable structures. Perhaps we'll find definitive proof of the Hercules-Corona Borealis Great Wall. Or maybe we'll discover something even grander in scale. We might observe that the cosmic web exhibits a certain periodicity or regularity, which would finally shatter the notion that its formation was purely random. Every new cosmological discovery doesn't just provide answers. It raises new, even more profound questions. What existed before the Big Bang? What lies beyond the limits of the observable universe? Are we truly alone in this vast, structured cosmos? The journey has only just begun. And the most monumental discoveries, the ones that will fundamentally redefine our understanding of reality, are still waiting to be made. Well, our journey through the architecture of the cosmos has come to an end. We've seen that the universe isn't just a chaotic soup of galaxies, but a magnificent, ordered structure, a cosmic web made up of filaments, walls, and vast voids. We learned about giants like the Sloan Great Wall and even the seemingly impossible Hercules-Corona Borealis Great Wall, which genuinely challenges the very foundations of modern cosmology. We realized this structure is held together by the invisible scaffolding of dark matter, and that its initial blueprint was laid down when the universe was still in its infancy. But most importantly, we've come to understand that this architecture isn't just a scientific fact, it's a profound mystery, a mystery that forces us to ask the deepest questions about the nature of reality, our place within it, and the very limits of human understanding. The greatest forbidden secret of the cosmos isn't some conspiracy, it's the sheer, incomprehensible majesty of its complexity and beauty, a beauty that strongly hints we are standing on the threshold of a new era of cosmic understanding. Thank you for spending this time with me, journeying across the vastness of the universe. I hope this discussion helps guide you toward a deep and restful sleep. And now here is the final question I want to leave you to ponder. What do you think truly lies behind this cosmic architecture? Is it just the random unfolding of physical laws, or is there something far greater at play? Share your wildest theories in the comments below. Don't forget to subscribe to the channel and hit the like button if you found this journey interesting. Good night.